Here's a number that should grab your attention. 500 watt-hours per kilogram. That's the energy density CATL says its next-generation solid-state battery is targeting at the cell level. For comparison, many of today's best lithium-ion cells sit around 250 to 300 watt-hours per kilogram. If that gap holds at scale, it's not a small upgrade. It's a leap. And this isn't coming from a startup with a prototype in a lab. It's coming from CATL, the largest EV battery manufacturer on Earth, responsible for roughly 1 out of every 3 EV batteries produced worldwide. This isn't just about better range. It's about who controls the most important component in the future of transportation. Tesla, BYD, Toyota, Volkswagen. They all know solid-state batteries are coming, but none of them control this one. Let's break down what's really happening and what changes if CATL delivers. Before we dive in, subscribe for deep breakdowns on the science and strategy shaping energy and tech. Most people know Tesla. Very few know the company that powers much of Tesla's fleet. CATL, Contemporary Amperex Technology Co. Limited, was founded in China in 2011 by Robin Zhang. In just over a decade, it became the dominant force in global EV batteries. Tesla uses CATL cells. BMW does. Mercedes does. Volkswagen, Hyundai, Honda, the list goes on. When a new automaker launches an EV, one of the first questions isn't about design. It's, who supplies the battery? And very often, the answer is CATL. Here's what makes that important. Most companies can invent a breakthrough in a lab. Very few can manufacture it at massive scale. CATL operates more than a dozen major production facilities and supplies over 30 countries. It has already mastered lithium iron phosphate chemistry, high-nickel lithium-ion structural pack integration, cost-down manufacturing at enormous volume. So when CATL announces new battery chemistry, the industry doesn't treat it like a science experiment. It treats it like a countdown. To understand why solid-state matters, we need to understand what's holding current batteries back. Every EV on the road today uses lithium-ion batteries. They work well, but they have structural limits. First, safety. Inside every lithium-ion cell is a flammable liquid electrolyte and allows lithium ions to move between electrodes. Under normal operation, it's stable. But under heat, damage, or manufacturing defects, that liquid can ignite. If one cell overheats, it can trigger neighboring cells in a chain reaction called thermal runaway. EV fires are rare, but when they happen, they're difficult to extinguish because the reaction is self-sustaining. Second, charging limits. Using 350 kilowatt fast chargers, but most EVs still need 25 to 40 minutes for a meaningful charge. Why? Because the battery itself limits how quickly ions can safely move without overheating or degrading the cell. The charger may be fast. The chemistry says, slow down. Third, energy density and weight. At the pack level, most EV batteries deliver roughly 150 to 220 watt-hours per kilogram. That's why a large battery pack can weigh 500 kilograms or more. More range means more cells. More cells mean more weight. It's a balancing act. And finally, degradation. After roughly 1,000 to 1,500 full cycles, many lithium-ion batteries lose about 20% of their capacity. They're still usable, but range declines. These aren't engineering oversights. They're chemical constraints. So what changes with solid state? The difference sounds simple. Replace the flammable liquid electrolyte with a solid material, ceramic, glass, or sulfide-based compounds. Ions still move between electrodes, but now they travel through a solid layer instead of a volatile liquid. No liquid means dramatically reduced fire risk, but the advantages go beyond safety. Without liquid electrolyte, engineers can potentially use lithium metal anodes, increase energy density, reduce cooling requirements, simplify pack structure. That's where the 500 watt-hours per kilogram number comes in, again, at the cell level. If even part of that translates to the pack level, you could see significantly lighter vehicles, smaller battery packs with the same range, or dramatically longer range at the same weight. But here's the important reality check. Solid state isn't magic. It has challenges. One of the biggest is interface resistance, the contact between solid electrolyte and electrodes. Another is lithium dendrite formation, tiny needle-like structures that can form during fast charging and cause short circuits. Some solid electrolytes are brittle. Others are sensitive to moisture. So while solid state offers enormous theoretical advantages, scaling it reliably is incredibly difficult, and that's where most companies stall. Toyota has been researching solid state for years, so have Samsung SDI, QuantumScape, and Solid Power. But here's the difference. Most solid-state breakthroughs exist at prototype scale, small batches, controlled conditions, high cost. The gap between a working lab cell and millions of automotive-grade cells rolling off production lines is massive. CATL already operates on the other side of that gap. It has gigafactories, global supply chains, long-term material contracts, automaker partnerships ready to adopt new chemistry, and importantly, CATL is not promising an overnight revolution. The company has indicated a phased rollout. First, semi-solid state designs, hybrid cells that combine solid and liquid electrolytes, then gradually moving toward fully solid architectures. That staged approach matters because the industry can't absorb sudden chemistry shifts. Vehicles must be redesigned, software recalibrated, thermal systems adjusted. CATL understands industrial transition. That's what makes this credible. Not just the chemistry, but the manufacturing discipline behind it. Let's assume CATL successfully scales high-density solid-state cells. What changes? First, range flexibility. You could build an 800-kilometer EV without adding massive weight, or build a lighter 400-kilometer EV that's cheaper and more efficient. Second, charging potential. In theory, solid electrolytes allow higher thermal stability and potentially faster ion transfer. But real-world charging speeds will depend on solving dendrite suppression and interface resistance at scale. If those hurdles are cleared, 10 to 15-minute meaningful charging sessions become realistic. Not guaranteed, but realistic. Third, longevity. Early data suggests some solid-state chemistries could improve cycle life significantly, but long-term durability in real-world automotive conditions is still being validated. Now here's where it gets strategic. If CATL controls the most advanced, scalable battery chemistry, the leverage shifts. Automakers still design vehicles, but the company supplying the defining technology gains enormous negotiating power. We've seen this before. In smartphones, chipmakers like Qualcomm and manufacturers like TSMC became gatekeepers of performance. The same dynamic could emerge in EVs. Not total control, but influence. And influence at this scale reshapes industries. Solid-state batteries have been 5 years away for over a decade. What makes this moment different isn't just the chemistry, it's who's building it. CATL already supplies a third of the world's EV batteries. If it succeeds in scaling solid-state, even partially, it doesn't just improve EVs. It changes the balance of power inside the entire automotive industry. The question isn't whether solid-state will arrive eventually. It's who will scale it first, and who will be forced to follow. If this breakdown helped you understand what's really at stake, subscribe for more deep dives into the science and strategy shaping the future of energy and transportation. No hype, just clarity.